When we did our sample versus our population, remember your sample mean versus your population mean, right? So what does S stand for in our sample? Standard deviation. When we see S. And in population, it's the little sigma sign. Variance, therefore, would be standard deviation squared, and the population would be sigma squared. This little part that we're doing now deals with these two things. So you might want to write down what we call for our sample standard deviation, and you make an inference excuse me, about our population standard deviation. Our variance is our standard deviation squared. We're going to start with that and then break it down. So how do I go from a square to not square? Square root. So we're going to have a formula that's going to have s squared in it, then make it squared in it, and then we're going to have sigma squared in it, and then we're going to take the square root to get it without the square. So it sounds real bad, but it really isn't.
Sounds wild.
So the point estimate that we're using this time is not the x bar, not the mean, not the p. We're using an s or an s squared to make an inference about our population. Remember, we do a confidence interval to make an inference to see where the population one would fall between with our little extra wiggle room. Now, a chi-square has degrees of freedom. See all the little curves? That's even on your note page. It's a really good note page this time. So you see all the little degrees of freedom out here? The one thing that I want you to know is this doesn't follow your normal curve. It goes from 0 to infinity. There's no negative z-scores. There's no negative t-scores. There's from 0 to infinity. It's where these little scores are going to come from. And it comes off of table 6, which I forgot to Xerox for you, but we'll use your book for the meantime. So the bad part is, it always looks at the area to the right, not the area to the left. But we're not going to let that affect us, nor are we going to let it change our minds of thinking, because I want you to always think area to the left. So we do this slightly different. So we call this chi-square, and in your curve, it's greater than or equal to 0. All your values are positive from 0 to infinity. You have your family of curves. Underneath the whole curve still equals 1. All of them are skewed to the right. The tail goes to the right. It means the higher end goes like this, to the right, no matter how big the curve goes. You really don't have to know that part, but it helps to get an understanding of what we're doing. It's different for each degrees of freedom, like the other one was with our degrees of freedom. And the most critical part is finding these two values. We need to find a chi-square right and a chi-square left. And we're going to do that from table 16. This is the toughest part. Now, they give us these two little formulas, which I gave you on the bottom. However, we're not going to really use those. Well, we do use them, but is that your phone? It would be nice to shut it off. Okay, so now, we're going to do it a little bit differently than they do. We need to find the critical values for a chi-square left and a chi-square right. It can go like a family of curves. So this would be the left-hand side, right? This would be the right-hand side. So isn't the left-hand side value lower, less, L, left, lower, less than the right-hand side?
Right.
Good. So now, this is how we do this. For a confidence interval of 0.95, they work it a little bit backwards, but we're going to do the same thing we do for all our inverse norms. We're going to say 1 minus 0.95 divided by 2. We can't do it in your calculator, though. So, in your table. So this is 0.05. Divide 0.05 in 2, and you get 0.025. What is 1 minus 0.025? 0.975. Okay? So, these are the values in table 6 that we're going to look up at the top. We're going to look for these values. We don't care which one is right or left yet. We're going to figure it out ourselves. Table 6, they give you a little excerpt in your book. And then we can read the table in the back until I copy it. So take a look at page 331. See how they highlighted? On the top, 0.97, that column. 0.025, that column. And notice the left-hand column says degrees of freedom. So if our sample size is 18, what is our degrees of freedom? So you're going to find on your top. We don't care which one this is yet. We're going to figure it out. You're going to tell me this value and this value. Now, before you do, which one should be smaller, the left or the right?
The right.
And
No, the left.
the left, because doesn't this go from 0 to the greater?
Yeah.
Left, less, lower, least. So, out of those two numbers, the smaller number is the left-hand number. So, out of those two numbers that they intersect with, which is the lowest number? Thank you. And then the other number?
30.199.
199?
191.
191. So now, we found the chi-square right, we found the chi-square left. Okay. Technically, it's got a reverse look. Technically, by doing this, we actually find the upper one. And then we subtract it and find the lower one. But I don't want you to worry about that. All I want you to do is the same thing we usually do for inverse norm. 1 minus the confidence level divided by 2. And if you open your back of your book to page A18, sorry, A19, you'll see your page. Now, don't write in your book, but when I give you this table, notice the center of this table. Put your finger where you think the center is. There's what, 5 to the right, 5 to the left? Is that the center?
Yeah.
5 to the left, 5 to the right. Notice where your center is. You see where the little alpha sign is?
Yep.
Okay, now, go symmetric. If you would like to do this, 0.90, 0.10, 0.95, 0.05. See how they're symmetric? They go like this. 0.90, this is technically the center. 0.10. 0.95, 0.05. See it? Don't those add up to 1? So it's an easy way to find your numbers. But that's not your confidence level. First we have to do 1 minus your confidence level divided by 2. Don't fall into that trap. We don't have that confidence level. Do you ever have a confidence level that's 0.005?
No.
No. You might have one that's 0.95, 0.99. You never have 0.975. You never have 0.005. So therefore, the first thing we have to do is this piece. Just like you did inverse norm, but no calculator. Then find the corresponding one, left side, right side. The left side is the least. All right, let's try another one. This is the whole thing right here. So now, we need to find a confidence. Again, here's my curve, slightly skewed to the right. I've got an x2. You write these guys, it goes like this, like a squiggle and a line. x2L and x2R. Chi-squared left, chi-squared right. So, if our sample size is 30, what's our degrees of freedom?
We have to draw it. 29.
Well, it kind of helps you figure out where the left and the right go right now, because this is going from 0 to infinity.
29.
Okay? And here's my confidence level, 90. So I first have to do 1 minus 0.90 divided by 2. I suggest you write this down somewhere. This is the most important part. So you get 0.10 divided by 2, 0.05. What's its counterpart to 0.05? 0.95. So now, you're going to look in your table at 0.95, at 0.05. You're going to come down to your degrees of freedom of 29, and you're going to pull out these two numbers.
17.708.
So which one is that, the left or the right?
The left.
Because it is
Smaller.
smaller, 17.708. And what's the right?
42.552.
See how we find those?
Says 17.768.
708 or 68? 68? Joey, what is it?
08.
Oh, wait. Where's my book?
That's 2 on.
0.95?
I got it.
1708.
You don't want to told you.
1708. 708.
That says 557.
And that says 42.557. Can you guys find that on your charts?
I can. Yeah.
Okay? So everybody find me 95% confidence interval for a sample size
Oh my god.
of 15.
Is this the same one with the holes poked in, or are there a couple?
What?
The calculator.
I don't know. You tell me. You picked it up. I'm not looking at it.
Because
You're the one looking at
I
it.
picked one up the other day.
Let me use my X-ray vision.
Come on, kids.
All right. Find me the X2L. Tell me which one's the X2L.
Yes.
Tell me which one's the X2R. Tomorrow I'll have this table copy for you.
Wait, do we put in the inverse norm, or
What did I say? What did I say 3 times already?
find the x to r?
You cannot use inverse norm, but we set it up the same way we go to do inverse norm.
So what do we do? Just regular
We do. Tell them what we do, guys.
vanilla?
Joseph,
Tell them, Paul.
parentheses, 1 minus the confidence level divided by 2. I think Paul's gonna
Thank
tell
you, Paul.
Hey, Paul, you know what? Thank you.
So you find me the answers to this.
Found them. Coach.
What's the right one?
Oh, the right one. Oh, hold on. Let me curve all there. Yeah, the left
But
one.
we do 1 minus and
26.
1
and minus.
and minus
Is
1.
it 26.119?
I don't know, guys. Is it 26.119?
Yeah.
The right one you said.
Yeah,
The right one.
it is.
You find it on your table?
That's the left.
What's the left?
5.629.
3.816. Shoot. 3.816.
I got 5.629.
What did you look up on the top? 0.025 and what?
Oh, I did. No, I went to for degrees of freedom. I went to 11 for some reason.
Got to go to n minus 1, 14. Can everybody find these? You find them?
Yeah, I know.
All right. This is the hardest part of the whole thing.
You said the left is the small one, right?
The left is the least. Go by the L. L, least, less, lower, left.
So then, so
Because this is your left-hand side. This is your right-hand side. Look where the numbers go. The numbers go from 0. That's why I want you to draw the chart.
no, I'm saying, wouldn't 0.025 make it less since that's lower than?
Yes, it would. Because chi-square does the reverse of what we normally do. So I don't want you to get hung up on the 0.975 and the 0.025. All I want you to do is look at these two and place them in here. And that was a very good thing that you noticed, because normally our z-scores say area to the left. Our chi-square says area to the right. So that I don't make everybody confused with z-scores and then they never remember z-scores for me, I say don't worry about who's left and who's right now. Just do it this way. Pick the larger number on the right, pick the smaller number on the left, because it works the opposite of what we normally think. So very good. Now, to build a confidence interval, We're going to build our confidence interval like we build an inequality, which really is what your confidence interval is. It looks bad, but watch. This is the guy you just found. Did you not just find that? What is n minus 1?
That's the
Degrees of freedom. What is s?
That's so the thingy. When you put it in the
This happens to be the variance s squared for the sample. So either they're going to give you a sample variance, in which case you're going to replace s squared, or if they give you a sample standard deviation, then you have to put in the s and you have to square it. That is probably the only difficult part, is when the word problem will say, and the sample standard deviation is, the sample variance is. Now the reason we do all this for variances and standard deviations is this. They don't work like the regular numbers. We can't make means out of these. And you know how you find the mean of something and then you find the standard deviation? Well, say I took this calculator and say I want to know these little screws in the back that hold this back door on here. They can't vary that much, can they?
no.
Because then they wouldn't hold it tight enough. It wouldn't fit inside the hole. It wouldn't even stay inside the hole. So there's very little variance, very little room you could make for this. So if you were to do the mean of how, let's say, wide these things are, or maybe the radius or the circumference or whatever we're looking at, it would be such a small number, and it can't vary by that much. Even like things like the buttons that go in here, they have to be a certain size or they're not going to click, right? They're not going to have any more room. Too much and they'll wiggle around and fall out. So these are things we use for variances, things that have very, very small measurements, because we can't take a mean with the standard deviation. It would be way, way, way too small. So they call this a chi-square. Now, when we set this up, notice the numerators are both exactly the same. The denominators you just found. But notice the right one is now on the left-hand side. Does anybody see why?
It's the opposite.
Because it's
Right and left.
the lower confidence.
Okay, so why do I put my larger number? So what was our last two that we found?
They were 5.629 and 26.119.
Okay, so why would we put the larger one on the left when we make an equation? In our graph, it
So
went like this.
So it's positive.
No, they're both positive.
So it's the chi.
No? I just want to know why isn't the left over here? Why isn't the right over here and the left over here?
Because math.
Because math. Because why?
Class dismissed.
Because why? If I divide something by a larger number, don't I get a smaller answer? And my inequality, which is my confidence interval, doesn't it go small to medium to large, right? This has to fall in between these two numbers. This has to be the smaller, this has to be the larger. Agree?
Mm-hmm.
So this is why we put the right one on the left-hand side in the equation and the left one on the right-hand side, because that's a smaller number. That will give us a bigger answer. You'll see it when we put the whole thing together, if we can keep Paul awake. And all we do for this, is take the square root of everybody. Once you find your answer, you just say square root, square root, square root. Okay, so let's do one together.
No.
Joe, stay with me here. Uh-oh.
I am awake.
My board is acting up on me.
Oh my lord.
I know.
Man, all white.
Here's one. Okay. You randomly select and you weigh 30 samples. What does 30 represent? N.
29.
So degrees of freedom are 29. Shh. I don't want to hear a sound. Assuming that the weights are normally distributed, even though we're not using a normal curve, they need to have a normal distribution.
It's going to be 0.02.
You're given the sample standard deviation, What letter do I use to represent this? S. You want to construct a 99% confidence interval for the population variance and the population standard deviation. You want an interval so that you can be 99% confident that based on this sample information that your population standard deviation and variance will fall between those two numbers. Again, that's not changing. We still want to do it for that reason. So we have these formulas. I'm going to give you the formula, so you don't have to worry about the formula.
Is that the same thing as like what we did, but on here? Is that just an easier way of doing it?
It's the same formula.
So it's just an easier way of finding instead of using the table, right?
We didn't use the table yet. We have to use the table now to find these guys, which are x2r and x2l.
So the number 52.336 would be the x2r?
Okay, so what did you use on the top?
0.005.
Good. So we start with 1 minus 0.99 divided by 2. So this is 0.01 divided by 2, 0.005, 0.995. Degrees of freedom are 29. So Joey already told us. You guys look it up first, and then we'll confirm with Joey.
13.121 and 52.36.
Okay, let's make sure they have a chance to look it up. So hold you got it.
I don't have any horses.
I didn't say horses.
I read your mind.
I just said hold it.
What else is a phrase that says hold your what?
Hold your tongue.
Oh, she got you there.
What?
Hold your
Man.
tongue. Right?
Hold your peace.
Hold your tongue. Alright, so you guys look this up. You have to be able to do this. This is the whole confidence interval. You're staring at it. Remember, the one on the left is going to be lower. We find it here. However, in our formula, we're going to have to put the larger one where the right one goes.
52.336 would be the
52.336.
Oh,
would be
wow.
would be the right.
Yep, it would be the right one.
Finally know what's going on.
So, Sean, what's the left one?
Oh,
But the left one goes on first, right?
hey, Joey, do you mind? Thanks.
Ask me a
Thank you.
question.
Tell him to hold his
It's,
tongue.
13.121.
13.121.
Piece back there.
I'm gonna fight you.
Okay, shh. Now look, guys. This is how simple this is. It looks horrible, but you know your degrees of freedom. Degrees of freedom are 29. Your sample is 1.20, and because it's a standard deviation, we square it. That's the same numerator on both sides. 29 times 1.20 squared. So all you have to do is put it in your calculator exactly the way you read it. 29 times 1.20 squared divided by 52.336. Just like you read it. There's no trick to this. It just looks real bad.
And then it's one.
Do we put
one-
anything in for the standard deviation?
1.20.
No, in the middle.
Nope, that's you know when you do your confidence intervals and you go like this, but I said you can do this with the mean in the middle.
Yeah.
We build it just like this.
Oh, okay.
We don't do it with the comma in this one.
All right.
So you should get 0.80.
Oh, that's pretty rounded.
Yeah.
Oh, okay.
Rounded generally to whatever your sample standard deviation is rounded to.
What did it say on the wall?
0.80 less than the sigma squared less than 318, 3.18. Now, again, I want to be 99% confident that from this sample, I know that my population weights of these medicines, for all the medicines of the allergy medicines or whatever they are, will fall between 0.80 and 3.18. I'm making an inference about the population based on my sample. Now, oh sorry, I said standard deviation, variance. To find the standard deviation, watch, all we have to do is this. Take the square root. Just take the square, put it in your calc, and take the square root.
Wait, that's not the answer?
Well, that's the first one, that's the one for the variance. You do two, you do variance and then you do standard deviation. So standard deviation is 0.89, 1.78. And I'm 99% confident that my standard deviation for the population of all allergy medicines will fall between 0.89 and 1.78. Remember, it's a standard deviation. For allergy medicine, it doesn't have to be really small. Really small. Standard deviations also don't have like a denomination, like grams, inches. They're like canceled out somewhere, so they're just plain numbers. So that's how easy it is. Now, the try it 2 says this. The try it 2 says, make a 90% and a 95% confidence interval for the things we just did. But we're going to do it in 2 parts of the room. Right over here, this part is going to give me a 90%. For the same information, the sample size is 30, but you have to find your sample standard deviation was 1.2. But you still have to find your X2R and X2L all over it. This side of the room is going to do the 95. What should we find out about the 95% confidence interval?
Narrower.
No,
wait, wider.
Wider.
Are you stupid, Joseph, or are you stupid?
Sean? And we're good with that? Again, if I put this on a number line, let's put this on a number line just for a minute. Here's your 90. I'll just do the standard deviation. 0.991 to 1.536. Here's this guy, 0.91. 0.95 over here. These shapes wider.
What one was that, the second? Very good. I like that one anyway.
Yeah.
Just smelled a lot. Smelled
Too loud.
Yeah, we're...
So do you notice that your point coming out here, guys, if this is 0.95, sorry about that phone call. Do you notice that your 95% one is wider?
Yes.
The same rule still holds. All right.